this video, I'd like to talk briefly about types of forecast statements. Now, the idea here is we're moving away from descriptive analytics, where we're just looking at correlation between variables, maybe testing some hypotheses about whether those relationships are there, and getting into predictive analytics. So we're going to start using things like a regression model to predict outcomes, either based on a set of covariates for a particular observation or based on time and rolling forward into the future to predict what might happen after the end of a sample of data, for example. Forecasts, just like what we're looking at in terms of how we describe the coefficients in a regression model, forecasts can be expressed in a couple of different ways that carry different amounts of information depending on what you're looking for. And we're going to make probabilistic statements about our predictions for what's going to happen or what has happened in the same way that we make probabilistic statements for the coefficients in a model by giving things like a confidence interval. So quickly we'll go through a few different types of forecast statements. The main ideas here are really just point and interval forecasts. Now I'm going to show you a couple of oddballs that are sort of compound forecasts, but fundamentally we should be able to boil everything down to these forecast types. All right, starting with the simple point statement, a point forecast about what yi should be according to a linear model, or about what the outcome should be, say, next month. Just like with the coefficients in a model, the first column in the regression output in Excel is going to tell you what that coefficient is estimated to be. That's your best guess, and it's just a single number, a single point on the real number line. You can do better than that. A single number is not so bad, but every one of these estimates, like beta 1 hat, comes with some uncertainty, but some measure of confidence or precision that is attached to it, and we'll stretch that into interval forecasts. So if I have a standard error for my estimate, well then of course I can put together a confidence interval using something like assume that it's a normal distribution and build a 95% confidence interval as your point forecast plus or minus 1.96 of the standard error of regression. That would be a great approach to building a 95% confidence interval forecast. And you see this a lot in real business data. You'll see things like a 90% interval forecast for the number of jobs expected to be added the next quarter is, we've got a lower bound, we've got an upper bound, and we're simply saying there's a 90% chance that the true number comes in between 150,000 or 200,000. Fair enough. The exotic sort of forecast would be a density forecast. So if instead of giving a point and an interval, I give you something really strong and I say it actually is normally distributed with a particular mean and a particular standard deviation or variance in the case of the normal distribution. The normal distribution, saying that it is normal, tells you everything there is to know about the shape of the possibilities, and saying the mean and the standard deviation tells you exactly which normal distribution that's going to be. The normal distribution only has two parameters. The shape is always the same, but there's something about the location and maybe something about the scale, right? So where is it centered on the number line, and then how far is it spread out around that number on the number line? Giving me these two numbers together with the statement that it is normal tells me everything about what could possibly happen, which is kind of cool, but also perhaps a bit excessive or a bit artificial if you don't believe that the different outcomes are actually normally distributed. This seems strange. Well, here's a picture example of what it might look like. You give a point forecast in the center. You assume that it's normal. Well, your interval forecast goes out to, say, plus or minus a couple standard deviations, and you've got all three here in one graph, a point, an interval, and then the density if you really want to make a statement about what the shape is. That's usually what we don't do. We usually just do points and interval forecasts. All right, fair enough. What about this guy? Well, let's see if we can break it down into points and intervals. This is a fan chart from the Bank of England, and they give their forecasts for things like inflation, CPI forecast based on market interest rate expectations in November 2014. And I do see this fan chart still in use, and sure enough, I did a conference at the Cleveland Federal Reserve Bank about 2 years ago, and one of the people on the same panel as me got up and started talking about inflation, and they had one of these reports from the Bank of England with the exact same fan chart using slightly more modern data, and it's kind of cute to see. Bank of England is a big deal in that arena. So what do we have? I've got some data. I follow the data, and at the end of the sample, it starts turning into these predictions. Well, in the red area here, the darkest red area, there's a pretty good chance that these numbers are going to occur. So maybe that's something like 60% confidence. And then the slightly lighter interval from down here to down here is maybe something like 80%. And then the one that's sort of a pink or a salmon color is perhaps 90% confidence. What we're seeing here graphically is compound interval forecasts. We've got points, intervals, and densities. We're using multiple intervals to try to get something a little bit closer to a density. So this interval here is very close to the point forecast. This interval here is a little bit further away, but higher confidence. And this interval from the lightest pink down here and up here is also higher confidence. Notice then that every month, every quarter, these are years and break it up into quarters. Every quarter, they have a different set of 3 intervals that are plotted in this fan shape. So there are a lot of different interval forecasts being represented as very complicated information or sophisticated information because it tells you a lot, and they're all just shown here in a graph. This is kind of nice, but it's fundamentally just interval forecasts. Well, how about this? Interval forecasts from the Federal Reserve Semi-Annual Report to Congress, February 2010. Figure 1, Central Tendencies and Ranges of Economic Projections 2010 to 2012 and over the long run. This is kind of fun. I see inflation. Okay. PCE, Personal Consumption Expenditures. What is this? 2010, I've got forecasts, and the forecasts have been boiled into box and whisker plots. So the box in the center of the box and whisker plot is supposed to account for 50% of the possibilities. And in fact, they used 12 separate point forecasts, and they gave us a box that accounted for the center 6 of those 12. Then the top whisker and the bottom whisker, if the box is 50%, the top whisker and the bottom whisker should account for 25% each, going all the way up to the maximum of the possibilities and all the way down to the minimum of the possibilities. Once again, they're essentially giving us a graphical depiction of multiple iterations of either points or intervals. Here, because we have 12 different points given by 12 different banks in the Federal Reserve System, we've got 12 different points boiled down to 3 up here, 6 in here, and 3 down there, which is essentially an interval. Those forecasts range from this number up to this number. Interesting, different way of doing things, but seeing the 50% in the middle and seeing the tails on either end kind of tells you something about the shape. So again, sort of looking a little bit more like a density, even though it's just a compound graphical representation of either points or intervals. There's something interesting about this one that they do 2010, 2011, 2012. So they're giving us different windows, different forecast horizons that they're predicting using data from 2009, right? This is old. But they also have this long run where they're saying, what do you think inflation will be in the long run? And here in 2012 and again in the long run, there is no top whisker. Why is there no top whisker? Because in fact, all of those point forecasts in the upper distribution are the same as the upper one in this middle 50%. So at least 4 of the 12 point forecasts given by 12 professional forecasters from 12 Federal Reserve banks are here at this number, whatever happens to be the top of this distribution. And it's cute because that number happens to be 2. So they're predicting that there will be exactly 2% inflation. In this window of time, 2% inflation was the Fed's inflation target. So they're expressing their belief that in the long run, if there's too much inflation, the Fed will raise interest rates and lower inflation. And if there's not enough inflation, the Fed will lower interest rates and raise inflation. So they're essentially saying, by giving this precise forecast in the long run, that they believe monetary policy works, which for the most part is reliable. Although in the last couple of years, we have a lot to say about that. we'll skip it, but there's some explanation there for where those forecasts came from. Fundamentally, just graphical depictions of these three entities. The more information you give me, the closer I get to something like a density forecast. A point forecast is only one number, not a lot of information. Intervals can contain a lot more information. Give me multiple intervals, and we start getting closer to a density forecast, which tells me everything about the shape of all the possibilities. In terms of the frequency for how they're actually used in practice, this is not it. Point forecasts are the most common, then intervals, and then density, right? More frequent, less frequent, and very rare, okay? Least information, more information, and maximum information. So as far as this class is concerned, we're really just going to focus on point forecasts and interval forecasts. And the way that we put together a point forecast could be, well, let's try one. And then let's see if we can build a confidence interval using something like our point forecast plus or minus 1.96 standard errors, which would essentially be the shape of the interval that a normal distribution would give us. Here I've got the orders data that we used in an old homework example. So what do I have? I've got orders in thousands as a function of month, and I see how it varies over time. Okay, all right, so it varies across time. And over here on the right, I had some regression results. I'm going to go ahead and grab the data analytics tool pack up here, data analysis, get the regression tool, and I'm going to re-estimate that so I can throw it onto a new worksheet. And I'm going to do some things with this data. So input y range. Y is the variable I want to predict using whatever combination of x's are available. So let's predict orders all the way down to the last observation. And let's predict it using month. Now, this is module 3. We're talking about forecasting. I want to point to month and talk about month a lot because month is simply a count variable. Orders across time could vary depending on a lot of different things that you could measure. One of the things about real-world data, and businesses in particular, is that the real world does have a time dimension, and very often you can use time to predict what is happening. So I'm going to model orders as a function of month, and then what I can do is I can roll this time variable forward to, say, 49 and tell you what will happen in the next month that hasn't been observed yet. So I can try to predict what orders will be in the future. All right, so I'll hit OK, and input range contains non-numeric data. Let me fix that. Got labels, and I do want residuals, so I'm going to click on the residuals button here as well. Then I'll hit OK, and here's our output. What can I do with this? Well, 17% of the variation in the data, 17% of the variance is explained by this model, which only includes a time variable, kind of interesting. There's the coefficient for month, very statistically significant, t-statistic over 3, and the predicted value for the first observation in this data set is 90.4218. Let's have a look and see if I can recreate that number. Now this should be beta 0 plus beta 1 times the observation number, which happens to be the same as the month number. So again, very convenient that we started counting here, 1, 2, 3, 4, 5. Let's keep that going. I've got 1, 2, 3, 4, 5 for these observations. I will say that the predictions that come out of a model like this are invariant with respect to whether your observation number starts at 1 or whether it says something like 1950, 1960, 1970, 1980, or perhaps 1951, 1952, 1953, 1954. You'll notice that the scale of those numbers is radically different, but we're essentially relabeling the x-axis on our scatter plot. These numbers are going to change if you change those the units on your time variable, but the predicted values like these should not. So for instance, I should be able to go to month and change all of these by adding or subtracting an amount to all of them, or rescale by multiplying by 12, dividing by 12, for instance, and running the regression again and see if I get the same predicted value. you will. Okay, so let's go ahead and nix this 90.42 and just make sure I remember where it came from. That should be equal to the intercept plus this coefficient times the observation number, which is right here. And I'm going to hit equals, and I get 90.421769. This is the right number. I'm very, very happy. I'm going to make sure that these this B17 here doesn't move, and that B18 next to it doesn't move when I click and drag this down. All right, and then I'm going to say, will I still get 90.817? Yes, I did. If I delete these and then fill them in by extending my formula, do I still get the same numbers? Looking good so far. So I'm going to double click and send that all the way down. Now I've got predictions. And one thing I could have done that I didn't do here when I run that regression is I could have asked for the line fit plot, which here we go, where I can see that every month my prediction is increasing by the same amount. How much? Well, 0.396. My prediction will increase every month because there's this upward slope, and I would imagine stepping out into the future the prediction continues along that line. That's exactly what it's going to do. So I'll scroll all the way down, 46, 47, 48, and guess what I could do? 1 month out of sample. What will it be? 109.4. I can go to 3 months out of sample and have 109.4. Don't want the same 109.4. Let's try this. And let's verify why that happened the way it did. Because I said 49. Gotcha. Well, this is 50, and this is 51. Much better. Now, if I do it correctly, 109.4, 109.8, 110.2. Sure enough, I now have 3 point forecasts for the next month, the second month out of sample, and then 3 months ahead. I have now predicted what my orders will be. Now that's separate from whether this is a good model. It's probably not, but it's easy enough to work with. Let's go ahead and come up with an upper bound and a lower bound. I'll say lower, and then I'll say upper. Now, what will my upper and lower bound be? Using the regular formula for a confidence interval, it'll be my prediction plus or minus 1.96 standard errors. So I'll go ahead and comment up here that this is 95% confidence. All right, so we're doing 95% confidence interval. This should be equal to my prediction minus, in this case, because it's the lower bound, 1.96 times what standard error should I use? The standard error that corresponds to the size of the residuals. That's the standard error of regression. This number here tells you how large a typical residual is. That's the one to use. I'm also going to go ahead and throw some dollar signs on that B7. Don't move that. Really only need it on the 7, but that's fine. Because I'm going to extend this all the way down. Let me hit Enter, and this lower bound should also increase by about 0.4 every month. Does it? Sure enough. Now I've got lower bounds. They also trend upwards. And 3 months out of sample, at month 51, which hasn't happened yet, my point prediction is 110. My lower bound is 86.19. Let's make upper bounds. I'll go ahead and grab that formula right there. Gonna need that. I'll drop it over here in the upper bound category, and then I'll just change my minus to a plus. Much better. Double click and send it all the way down. Now I've got a confidence interval. There's a 95% chance, according to a normal distribution, that whatever happens in the first month will be within this range from 66.395 to 114.448. And as I scroll down, look what I've got. 1, 2, and 3 months out of sample going into the future, so it's literally a forecast. I am predicting 109.432, so $109,432.62 worth of orders in the next month. Here's my 95% confidence interval, and here are 3 of them. So points and interval forecasts so far, not that difficult to do. reasonably straightforward. There's a caveat here. When we talk about an H step ahead forecast, H is like the forecast horizon. How far into the future do you want to predict? We have the option to predict a lot of different intervals here. H steps ahead could be 1, 2, or 3, which is what we just did. There's also something called an extrapolation forecast, where I say I don't want 1, 2, or 3, but I want all of them. And so essentially, I did just extrapolate 1, 2, and 3 periods into the future. Here's an H step ahead extrapolation point forecast, and here's an H step ahead extrapolation interval forecast. If I just say 2 steps ahead, this 2-step ahead interval forecast is just one of them. Sometimes you want all of those. All right, so the tools in order to produce point and interval forecasts are straightforward. What we need to do next is see if we can come up with a better model. I suspect that this model is just a little bit too simple to predict this data, but we will have some options as far as putting those together and then communicating that information for what we anticipate to happen based on a linear model, a quadratic model, or something more complicated is easy enough using things like point forecasts and interval forecasts. All right, I will stop this video here.